All right. So we're in chapter 5. I think today we're going to cover parts of sections 2 and 3. Which is pretty much all about definite integrals. So let's just remember where we left off. So we're focused on calculating areas. And we found a way to do it by forming a Riemann sum over the interval, which is an estimate of the area, and then taking the limit as the number of rectangles in our sum goes to infinity. So we took that whole process and packaged it up in this symbol, the integral from a to b. So all of that stuff is part of what we mean when we write this thing out. Later on this week, we're going to learn some pretty powerful technique to finding the value of that integral and therefore finding the areas as described. But before we get to that, we'll actually start it at the end of class today. I think it's useful for us to know, and it's helpful for at least one homework problem, and maybe more to come after today's class, to sometimes we can think about this the other way around. That is, we think we want to evaluate the integral to find the area. But sometimes, for certain functions, we can actually find the value of the integral by computing the area. We can do it backwards. Okay? Can't do it very often, but we can do it occasionally. And sometimes it's super helpful to be able to do it. So let's see how that works. Find the values by computing areas. And like I said, it's sort of backwards of the way we presented the problem on Friday. That is, we constructed the integral to help us find the area. And now we're going to use areas to find the value of the integral. We can only do it in very selected functions. But when we can do it, it's super handy and helpful to be able to do it. So I'm going to do 4 examples, starting with an easy one. Graduating to more interesting ones. Okay, so think about the function y equals 2x plus 1. Do we know what the graph is? Mm-hmm. Eric? Yes, and what is it?
It is a positive slope.
Okay, and a positive slope of
2.
So what shape is the graph?
Just a line.
Yeah, so that was so obvious you didn't feel the need to say it, and I agree with you, but I wanted you to say it. It's a line, and the slope is
2.
2, perfect, and the y-intercept is 1. So y-intercept is 1, the integral says go from 1 to 4. So the value of this integral is the area inside here, and if I draw a line through there, I see I can write the area as a rectangle and a triangle. Okay? I know how to find areas of rectangles and triangles. So the value of this integral will be their sum. How much area is in the rectangle? What's the y coordinate at this point right here? 3. Yeah. The picture guides us, but we use algebra and arithmetic to get the values. Yeah, we just plug in 1, and you get 3. So it's 3 units tall. How long is it? 3. So the rectangle has 9 units of area, and there's still a triangle under this function. So the triangle is 1/2. How long is the base? 3. How tall is it? What's the y coordinate out here? Yeah, and we said the y coordinate here was 3. So how tall is the triangle? 6. So the value of this integral is 18. Does that make sense to you? Did we evaluate the limit of a Riemann sum? No, we didn't. We found the value of 1, but we didn't do it that way. We know that that process gets us area, and we could find a more efficient way. Find the area. Okay? So this integral has value 18. Let's try this one. Too high. One plus the absolute value of x from -1 to 2. You know the graph of this function, like the absolute value. Yeah, it's a V shape. And all by itself, the vertex is at the origin. And what happens when we add 1 to that function? It goes up 1 unit. So here's our picture. Something like that. And we're going from -1 up to 2. So we need all of that as the value of this. Well, I can break each side of this into a rectangle and a triangle, just like we did over here. And I can find the area of those guys. Let me number them. We'll go 1, 2, 3, 4. So the area of 1, what is it? Yeah, it's a square, 1 by 1. How much area in region 2? It's a rectangle. How long is it? 2. How tall is it? 1. I can read that finger. 2 times 1. Right. I didn't label on my graph, but Ali told me, so I did it. The +1 just means we lifted up 1 unit. And if we believe this is 1, then it should be easy to believe this is 2. All right, region 3, it's a triangle. How long is the base? 1. How tall is that triangle? Also 1. Also 1. And then we have another triangle, the 4th region. 1/2 times the base is, and the height is 2, isn't it? So 3 plus 1/2 plus 2. So the integral -1 to 2, 1 plus the absolute value of x is 11/2, the value of the integral. Okay, questions? Let's see. The integral from -2 to 2, the square root of 4 minus x squared dx. Do we know the graph of the square root of 4 minus x squared? hope someone does. Nobody?
It's like,
Eric, show us what you did first with your hand.
Well, I
No, show us.
Okay, well, I understand
Oh.
that x squared minus 4 would create a steep v. And so I was trying to understand was the square root part.
Okay, but if you're trying to make a parabola, it should be going down, isn't it? Yeah. Well, put a square root over it, which kind of changes things. It's not a second degree polynomial, right? Because of that square root. It's a semicircle. I'll draw a picture over here. Just in case you can't tell it's a semicircle, I'll write the word. It's a semicircle. I hope we talked about that earlier. It's really helpful here because
oh,
the radius is the square root of that number. So just like I've drawn 2 to negative 2. So the value of this integral is the area in a semicircle of radius 2. Well, how much area is in a full circle? Radius 2, which is 4 pi, but this is only half circle, so what do I do?
over 2.
Yeah. So the value of that integral is 2 pi. Okay, is it making sense to you? Now, this is not the normal way we're going to operate. Normally, we'll have an area that geometry cannot tell us the answer to. And we'll learn a technique. We'll learn it on Wednesday. We'll start it today, finish it on Wednesday. That will tell us exactly how to do it. But sometimes, and this is not common, but when it happens, like, it's super nice. In fact, some of you already know the result that we're going to learn today and finish on Wednesday. But you can't make it work on part C. I'm trusting. Maybe you could, but it would be the rare student that could, in my experience. And same with part B, like the trick we're going to learn, it doesn't tell us what to do with the absolute value function. So you can't do it. I mean, you got to do something, you got to modify it. But here, if we just think of it, well, area, it's just rectangles and triangles. No problem. I promised you 4. Here's the 4th one. Oh, by the way, if this was minus 1 to 2, then we need to chop off this area over here. And we don't know how to do that from geometry. So I can't find the value of the integral. I need to know a little bit more about the process. So we're really lucky that it went from a radius to a radius, right? Across a diameter. That allowed us to use geometry to find the value of the integral. All right, one more here. Let's take 0 to 6. The square root of 9 minus x minus 3 squared plus 4.
Zero to 6. Okay. And that's the
So cover up the plus 4. Focus on the radical. What's the graph of that radical? What shape is it? Compare it to part C. What shape is it? It's a semicircle. What does the x minus 3 do to it? Pardon? Which way? To the right, absolutely, 3 units. The value that makes it 0 is going to be exactly like 0 was on part C. So it's going to shift it 3 units to the right. What's the radius? 3. So we shift the center 3 units over, and then we go from 0 to 6. That's like from a negative radius to a positive radius, right? Which means geometry can do it for us. Finally, what does the +4 do? We'll set up 4 units. So the graph is something like that. 6. And so the value of the integral, I have a semicircle and I have a rectangle down below it. How much area is in the rectangle? (24), 6 by 4. The full circle, radius 3, has how much area? Nine pi, did you say? But we have a semicircle. So divide it by 2. So the value of that integral, 24 plus 9 pi divided by 2. Okay? So occasionally, I'll say maybe rarely, but when it happens, we'll definitely take advantage of it. We can find the value of the integral because we know the area. And that's not how we asked the question on Friday. It's kind of working backwards, but we see that it can happen. And if you've done the homework, you've already done this. Sort of. All right, if you haven't done it, now you should be able to. Properties. I hope that's working. So everything we've talked about, limits, sums, derivatives, indefinite integrals, as soon as we define what they are, we list a bunch of properties they satisfy, right? And we've seen a couple properties show up on every single list. And it may be true here as well. And then some that are unique to the sort of thing a definite integral is. So what do you think one property might be? Just take a wild guess. Ever get a wild guessing? Okay, we'll list it. This is not the one I thought you might say, but it is one. If f of x is bigger than or equal to 0 on a closed interval, then the integral from a to b, which is a number, it's a positive number. Okay. We'll list it first because Carmen suggested something. She said the word positive, which made me think of it. Now this is unique to definite integrals. We didn't have any property like this for any of the other things. I mean, derivatives are functions. And we don't really talk about it being positive or whatever. But every single thing we talked about before, we applied to a sum. And what did we find out? The derivative of a sum is? The derivative. The limit of a sum is? You can say it. An indefinite, an antiderivative of a sum is the, yeah, it works every single time. And it works here. The integral from a to b f of x plus g of x is the integral from a to b f of x plus the integral from a to b g of x. Next one.
I'm guessing it's also multiplication and division.
Pardon? Michael?
I'm guessing it also works for multiplication and division then.
Don't guess too far.
Okay.
I can go with the first thing. So every time we listed this property, for all the things we talked about, what's the very next one we listed? A constant multiple. Yeah. And guess what? It works here. The integral from a to b of a constant times f of x is the constant times the integral. An integral is the limit of a sum. And we know that we can pull constants through sums, and we know we can pull constants through limits. So we can do it for an integral. Now I could pick the constant to be -1 and apply it to the function g here, and I get that the integral of a difference is the difference of the integrals. And that pretty much is what we've been able to do on all the things we talked about. Okay. I think the rest of these are unique to definite integrals, just like the first rule that Carmen suggested was. So let's see. The integral from a to b of x dx. So what I'm doing here is I'm flipping the limits around. So far we let symbol a mean the left-hand endpoint and b being the right one. Some things we'll do later in the week could cause those guys to get flipped around. And we want to know, like, what do we do? If the big number is on the bottom, like, is that a problem? And the answer is no. You just need to change the sign if you want to get it back. So the small number is on the bottom. Okay? Yeah, we're not proving all of these, but it's true. If I have the big number on the bottom, then my formula for delta x is going to make it negative. And that negative I could then factor through the whole process, the sum and the limit, to get a negative integral. Number 5. The integral from a to a. What do you think that ought to be? Eric says 0. Agree or disagree?
Agree.
Agree. Okay. I'm convinced. 2 people. They're exactly right. 0. There's no area above a point. Got to have some width to our interval. Rule 6. If c is a number between a and b, then the integral from a to b f of x is equal to the integral from a to c plus the integral from c to b. So a picture here is worth at least 183 words. So I can break this whole area, represented by the integral on the left, into 2 pieces. The first one represented by this integral, and the second one by that one. It just makes perfectly good sense. We already did this on the absolute value of x, right? We broke it into 2 pieces. And that, we didn't do it explicitly because we didn't need to know the formula, because we just had triangles and rectangles. But we definitely took the whole area and split it into the 2 pieces. Found the area there. And no one objected to that, so I'm going to assume you were all perfectly fine with it. And now you can see it written a little bit more abstractly. It actually doesn't even matter if C is between A and B. It still is true. Okay, we may have to use rule 4. You know, the values could get mixed up, but it's still true. It's just easier to draw a picture if we require that. Any questions? All right. So given some function of x, I'm going to start at some point. Eventually, make it all the way up to b. I'm going to stop at some arbitrary value in between, call it x. Then I want to define an area function. Like this, we'll call it cap A. It's equal to the area, that's why I chose A. It's area under the graph of f of x. Starting at A, up to the x value we choose. So for this picture, a function A of x is equal to however much area is in there. And you can see as I slide x around, it's going to change the value of the function. Because the function is non-negative, actually positive, A of x is an increasing function, right? The further out I go, the more area I get. If it dipped down below the x-axis, then we would start taking area away. It wouldn't be an increasing function anymore. And therefore, because of what we know about integrals, the area function is how we get areas. It's the integral from A up to x, integrating this function, but need to be just a little bit careful here. I don't want to write f of x. I've already said what x is. It's my right-hand endpoint, right? So I don't want to define it to be something else. So we're just going to give a temporary variable on this interval. We'll call it t. So t takes me from A up to x in the integral notation. Okay, and let me say a word or two more about that before we move on. The variable of a definite integral is a dummy variable. It doesn't matter what we call it. The only thing that matters is what is the function and what is the interval. Earlier today, we calculated, help me out here, 1 to 4, 1 plus 2x. Did we get 18?
Mhm.
Okay. What do you think the value of this integral is? Is it the same function? Is it the same limits? Yeah, so what's the value?
18.
So you see what I mean? The variable, doesn't matter what we call it. One thing that matters is what's the function and what are the limits? If I change the limits, if I go from 1 to 5, well, that's going to require us to do another calculation, right? We can't use this one. Or maybe we could use it and then use the property we just talked about and find the area from 4 to 5 and add it on, right? We can do that. But it doesn't really matter what we call the variable. And this is actually a t. I kind of botched it up. Okay, so I define an area function. I say it in words what it is, and then I can write an integral. You agree that I found the right one. Okay, now I want to really dig into this function, big A. In particular, what's big A evaluated at little a? Julian? It looked to me like you were trying to answer me. Not trying to pick on you if you weren't. Carmen, we am picking on you. 0, absolutely. So tell us how you realize that. There are 2 possible answers. Correct answers. Yeah, so there's no area above a point. The other way is you could say, well, property number B, I don't remember, one of those properties, and you could look it up, said that this is always zero. Okay, so one way or another, we get there. And notice that big A of B is the integral from A to B, which maybe is what we're really focused on. And now I can use X as a variable because it's no longer my upper limit. Because I'm going to go clear across the interval I'm interested in. A all the way out to B. I could use T, variable doesn't matter. The differential, you can see the dx, sometimes it feels like kind of a worthless appendage, but it tells me what the variable is. And that can be really useful. All right. So what I want to find out is, what is A's derivative? We define a new function. It's a function defined in terms of areas. The area is constructed in such a way that we can relate it to a definite integral. And now, because this is calculus and we have a brand new function, like it's only natural to wonder. Maybe some of you are already wondering, what is its derivative? Well, maybe not. That's probably too much. But I can ask the question, and now you can wonder about it. Like, what is A's derivative? Well, the function f could be anything whatsoever. So we're not thinking derivative rules. We're thinking about what does it mean to be a derivative? And let's just remind ourselves. We haven't had to mess with this for a while, but we never forget it. Applied to the function x, it's the limit as h goes to 0, a of x plus h minus a of x divided by h. Okay, and did you hear what I said right before I write it? Like, we never forget it. We know what the derivative is. Okay, and if maybe you did forget it, then don't tell me, then just remember it now. And it would be really good to have some easy question on the final where you get to show the definition of the derivative. We'll talk about that later. All right. So the fact that this f could be any continuous function whatsoever, it means can't get real specific information, but maybe we can find out some facts about it. And it means, like I said before, that the rules we learned in chapter 3, the product rule, the quotient rule, they're not really going to help us because we don't know what that function f is. Instead, we're going to think about what is a derivative. And there it is. And now let's just start and build up that expression. Okay, so let's first start with the numerator. Let me draw a new graph. Here's a big A of x is the area, starting at little a, working our way up to x. Okay? Big A of x plus h, for the time being, let's assume h is a positive number. X plus h would be up here somewhere. And so A of x plus h would be all of the area, starting at A, coming clear up to here. So the difference is just the area in that little slice, right? And I could approximate that. What did I do with my red pen? I'll see if blue.
Just right in front of me right here.
Ah, is there another one? Oh yeah, this student took it away from me. I could approximate that area with a rectangle. I'll draw it in red if this one of these pins is. So I'm going to pick a value in between x and x plus h, run him up to the function and draw a rectangle. So this guy is approximately equal to The area of that rectangle. How wide is that rectangle? H. How tall is it? Well, it's it's f of x applied to the point that I picked, right, to get the height. I'm going to call that x star. It's just I choose any old point, it doesn't matter, in that little interval. And so the functional value there, write it better than that. Where this x star is some number between x and x plus h. Okay. So let me clean that up and rewrite it, and then we'll move ahead. So a of x plus h minus a of x is approximately equal to f of x star times h. The area of a rectangle. Now remember, why we're doing this, we're trying to get information about the derivative. So we started with the numerator, and then to take the next step, I need an h down below. So what can I do then? Divide by h. And that's going to be approximately the functional value for the x value we chose, somewhere between x and x. Now, what do I do to get the derivative?
I'm gonna B minus in football. Oh no.
Sounded like Michael. Did you say?
Oh no, I didn't. I was thinking out loud.
So what are we missing? The limit. Right? We built up all the algebra. A of x plus h minus a of x is still on the board. It is. We divided by h. The only thing left is take the limit. So let's do it. As h goes to 0. What do you get on the left-hand side?
Just that.
0. So what am I trying to do? Correct. But there's a better answer. So look in the right-hand corner of the board. Take the limit as h goes to 0 of the expression we wrote. What do you get? The derivative. That's why we did all of this. We're trying to build the derivative up. Right? I reminded you what it is. So we started here, and then we incorporated h, and then we took the limit. And why did we do all that? That's what the derivative is. So I get a prime on the left. What about on the right? Well, as h goes to 0, we're being restricted on the x star we can choose. In fact, in the limit, what value is there to choose? Only x. Yeah, we're going to squeeze down on that x as h goes to 0. It's going to push x star in the limit exactly into x. We get f of x. The derivative of the area function for each x is the value of the function we're using to generate the area. Now, geometrically, that makes perfectly good sense. Eraser. Let me show you. Let's take a function whose graph looks like this. That's f. We'll start at a. Actually, let me make it even more extreme. Take a function like that. A, and then out here somewhere is b. So, what does the derivative of a function tell us about the function? It tells me the slope of the tangent line to the graph. What else does it tell me? Two things we think about what the derivative means. Ali said one of them, it's not the one I'm interested in. It's exactly right. Ali, good answer. Just not the one that I'm interested in. What's the other one? Not the derivative. Starts with R. You know, rewind back to September and start all over again. What does the derivative tell us generically? The rate of change. Give yourself a gold star. Now, let me pick this x value and this one. Call this one x1. At which value is the area changing more rapidly? X1 or X2? Why?
Because there's like greater amount of
Yeah, because f of x is bigger. What did we say the derivative of a is? The rate of change of the area is the value of the function. It's f of x. So when we have a small value, if I scoot up just a little bit, the area changes only a tiny little bit. But if I have a big value and I scoot up the same amount, then look how much area we get. So what we calculated over there is that the derivative of the area function is just the functional value, the function that's getting us area. If it's a little tiny thing, we get hardly any area. If it's a great big thing, we get a bunch of area if we increase x a little bit. Okay, that's all it says. The rate of change of the area, it depends on the value of the function we're using to generate the area. A little bit or a lot bit. Okay, I mean, I could have made this argument at the beginning and we would think, well, it's proportional. But no, it turns out it's exactly equal. We've done the work for every x. The rate of change of the area, this area function is exactly the functional value, the function that generates the area for us. Okay? So whether you can interpret it intuitively or not, that is, whether you understood what I just said or not, it doesn't change the fact that a prime of x is f of x. What does that tell us about big A? I'll give you a hint. Is n what's its relationship to little f? It's an antiderivative. Because when I take its derivative, what do I get? I get f, little f, right? And antiderivative. A little f. Why did I say n and not v? Did I make a mistake or did I know what I was doing this one time? Pardon? Yeah, if there's one antiderivative, there are infinitely many. Now, how do we know which one this guy is? Okay. Well, it's the antiderivative. I've erased it. That satisfies this condition. Big A of little a equals 0. Yeah. remember, didn't really put one of these on the last exam, but we did talk about initial value problem. Or we want to find an antiderivative that satisfies an exact value. There was a problem like that on the test, but it had constant acceleration, so you didn't need to rederive it. You could just use the formulas we worked out. Mr. Bannock.
So if it's A of A and it's like limit 2 to 2, maybe 0. Is that what you're saying?
Limit 2 to 2.
Yeah.
I'm not sure what you mean by that.
Like integral 2 to 2.
Oh, yes. Yeah, that's how we know that. All right. So the area function is an antiderivative. It's the antiderivative that satisfies the condition big A, little a equals 0. But it may be hard to know that given the function f. And so what we'd like to do is try to figure out how it relates to all of the other antiderivatives. I think we know how to find those. At least we've done some work in that direction. We have more to learn this week, but we know some things. And it's an unfortunate place to pause, but it's exactly where I got in the morning class, and I went like 2 minutes over. So on Wednesday, I'm going to keep you in suspense. On Wednesday, we're going to answer the question, how do I find the antiderivative that works for our function f? Okay? And then we'll state a result, which is called the fundamental theorem of calculus. And then we're going to practice it over and over.
So when do you have like any like office hours so I can like maybe have a FaceTime Zoom call or something for some
Are
extra
you
help?
available anytime tomorrow?
What?
Are you available tomorrow?
I'm available tomorrow, but I was having some questions over like the
Tonight's
I
assignment?
could go into the math lab, it's fine. But I think 5 to 7. Do about it.
I have a meeting at 3. You might try me. Is it at 3? No, it's at 4. It might. How about 3:30?
From 3:30 to 4?
Yeah, if I open
Or
the
around
window,
4.
could you join?
Hey, sweet, yeah. Just join the Zoom at 3:30.
Yep.
All right, thank you, sir.
Remember. See ya.
See ya.